Hello, good afternoon. I wonder if you can hear me. Please let me know if there's any problem with the sound from
I
my
can hear
side.
you well.
Thank you very much. Now, well, we're close to the end of a course, and I think we haven't done enough tests, but so I thought in a short quiz, and so there's a quiz up. If you look at the Moodle website, let me just point you to it. And if you scroll at the bottom, you'll see already two new sections. One of them is the, okay, let's see. You can put me everyone. Okay. So if you can see, there's two new sections. This one that says quiz 2, and those are the bottom of the website. So you need to scroll down all the way to find them. And here are the details. There's the details. And so the quiz will be released via Gradescope today at 4:45 p.m. So right after class, you'll be able to see the quiz and to download it. But once you download it, you'll have a 75-minute limit. Those people who are in need of who have the student right to get a longer time. Those that I know have been considered, but if you need that and you're registered, let me know. I think that 75 minutes is just more than enough that you would time it. It's only one problem, one single problem, one exercise, and two questions, well, related to it. A couple of questions. So it's a short exam, it's a short quiz. And so it's released today, but you can download it anytime between today and December the 9th on Thursday at 11 p.m. That will be the last time you can possibly submit your answers. So it will follow the ordinary Gradescope protocol. So you just download the template. And if you can print the template and give your answers on the template, that would be great. But you don't have to do that. If you don't have a printer, you can just write your answers on a piece of paper, any piece of paper. But please make it legible. And then after you're done, you should scan your answers and submit them through Gradescope in the usual way. So are there any questions?
I don't have a question related to the quiz, but today are we going over the knapsack problem with the Bellman equation?
Oh yeah. Oh, okay. I will. So if there are no questions about about the quiz, then by all means, I would like to answer your question. So who is it? Sorry, let me just get. Okay.
That was me.
Alvin. Okay, Alvin. How can I help you? What's your question?
I was saying, I think last class you said we would resume with the knapsack problem.
Oh yes. Yeah. Okay. So you wish that was my plan to resume with the knapsack problem, going over it, going through an example, and then and you may feel free to ask any question anytime you want. Is that what would that work for you?
Yeah, that sounds fine.
Okay. Sorry for this, but I had dental surgery today. and interesting. So, okay. Okay. So let's go. We were in our review of dynamic programming. Okay, here's the knapsack problem. We haven't gone through the knapsack problem, and it is one of the important applications or ways to apply the idea of dynamic programming on a practical problem. And the problem is really very, very simple. So you have a knapsack that can carry up to 11 kilograms. And you have different items that you would like to transport in your backpack. So here's a list for each of the items. You have the weight of the item, and we will use the symbol W, J for the corresponding weight for each of the items. And we also have a value for each of the objects. So not only does each item carry a weight, but also a value. And so the problem is how much can you fit in your backpack without exceeding the 11 kilogram limit, and at the same time maximizing the cost. It is because there are some items that might not be as profitable to take as others, but they may be very big, and so you want to solve this problem. Okay, and this is one of the natural ways in which we can apply the programming idea, because it is essentially a trial and error. So if you didn't know any dynamic programming at all, and you were just trying to go hiking and trying to solve that problem without the aid of dynamic programming, well, what would you do? Then you would have to just do trial and error. And it is that trial and error that is done by dynamic programming, only much faster. And in the end, it will ensure that you have the optimum solution, in the sense that not only are you within the limits of the 11 kilogram, but also that all the items that you have selected that you could carry are the maximum possible value that you could get into. There is no other combination that would provide a better value that would fit in your bag. Is that clear? Does that work for you, Alvin? I don't know. So for example, if you just take items 1, 2, and 5, and you have, so 1, 2, and 5, the object 1 is 1 kilogram, 2 is 2 kilograms, 5 is 7 kilograms. So you have 10 kilograms. So these 3 items would fit in your backpack, and you will still have 1 kilogram left. You still have room for one more item. I mean, for 1 kilogram item, but there's no other one. You have already taken the only one. So the only 1 kilogram item. And the value would be 1 plus 6 plus 28, which is 35 altogether. Okay. But if you take the set 3 and 4, you would take 3 and 4, then that's exactly the 11 kilograms. And we have a value of $40. So this solution, even if we are taking only 2 objects of 11 kilograms, is better than the other one, because it carries a higher value. So are there any questions for this? Can we proceed to see how to apply the dynamic programming idea?
Makes sense so far.
Okay. Okay. I was a little bit ahead of the slides. But let's say that you would like to apply a greedy approach to solve the problem, because that would be your first approach. Okay, say, well, what if this is one of those problems that can be solved with a greedy approach? That would be really great, because then I would just order my input. But now I have 3 ways to order my input, 3 keys for the sort. I can order them by item label, or I can order them by value, or by weight in ascending or descending order. And if I do that, if I sort my items by value, and then just repeatedly add each item with a maximum VI. So my sort would be a descending order sort. So I'm considering the elements from the heaviest weight to the lightest weight. So, and then blindly getting them into my backpack until I hit the capacity limit. I would have, for example, 7, and that would be added to the bag. Then what I would try to get this into, but it wouldn't fit because it's more than the 11. And then I go to the next item that would exceed the limit too, but I can get 2 and 1 and still be within the limit. And so my solution would be 1, 2, and 5. So what is the value for that solution? For 1, 2, and 5, I would have 28 plus 7, that's 35. So this is 35. So let's write it here. 35 is the cost or the value that we can achieve by, oh, sorry, that's what I did is by value. That's right, 35. What if I do the greedy by weight? So I start from the heaviest. Well, greedy by value in this case would be the same as greedy by weight, because they are at the same time. We have them. They keep the same order. So 1 is the smallest, then item 2 is the next one in value, and then this is the next one in value, the next one in value, and that's the next one in value. So you have this, the order in value would be the same as the order in weight. So we would come up with the same value. But if we do the greedy by ratio, let's say repeatedly adding an item with maximum ratio, we can also think on a ratio and make a sort by ratio. So let's do the ratios here. So VI over WI would be 1 by 1 is 1. 6 by 2 is 3. 6 by 5 is 3.72, or has it? No. 3.6. Okay, so this would be 3.6, and then this would be 3.66, and this would be 28 over 7, maybe 3.4. I mean, it would be 4 exactly. It would be 4 exactly. So the order in which these items are in ratio is also the same. We start with the maximum, which is this one, then this one, and this one, and this one, and it would arrive to 35 again. And what if we do not follow any of the above? Can you do better just by inspection? Can anyone tell me what would be a better solution than 35?
Technically, it would be the solution where you get 40.
How would you achieve it?
You would achieve it by doing the
What
that
objects
would
would you
be
do?
through item 3 and 4, right?
3 and 4? Exactly, that's right. 3 and 4. Oh no, the 3 and 4 you cannot, because 7 plus 6 is 13, and it exceeds the
That's 4 and 5, right?
that's 4 and 5. Oh, sorry. So 3 and 4. Yeah, that's right. 6 and 5 is 11. And yes, you have 40. Exactly right. Yeah, yes, Alvin. This is a much better solution than the other ones. But in this case, it is easy to see that it is the might be the best solution. But to be sure, you need to be mathematically sure. And so let's apply the dynamic programming idea, because the mathematics of the dynamic programming idea is what gives us the peace of mind that it has been mathematically proved that you would get the optimum solution. And so how do we achieve that? Well, we need to come up, as I told you before, with a notation, okay, to denote the subproblems. So dynamic programming works by considering a subproblem, so a partially solved problem up to some number of items, and which are the relevant, which of these possibilities is the subproblem that we should use. This is, let's say, a quiz for the class. Let me know. Should we use the OPT of W? So depending on the optimal value of the knapsack problem with weight limit W, or should the argument be I, the item label, or should it be I, comma W, the item and the weight? Or wouldn't any of these work? Just right out of the bat, what is your intuition? What is your idea? I'm asking for a guess, not for a right answer. So please feel comfortable to tell me.
C.
Okay. Oh, Becky, have you been reading ahead of the slides? Yeah.
No.
No? Well, you have a good intuition. You know, that's correct. That is exactly right. And why is it right? Oh, God. Oh, this is the point. If we were as naive as we had been so far, if we, with a simple problem like the one we analyzed in the previous class, we wouldn't need more than one parameter. It doesn't make sense to include more than one parameter for many problems. But it turns out that in this particular problem, we do need one more extra piece of information. We do not only need, note that if we get up to I mean, if we have the label I, it means that we can refer and we can get the weight and we can get anything else, but we need to know which item are we considering. I mean, up to which item are we considering, and this would be the remaining capacity, okay? The subject to weight limit W, okay? So so we would have, let's say, we would have to input an item and a weight. And this weight can be initially, should be the total weight, the weight limit, the 11 kilograms, but it can change. If you are, let's say you have the partial solution and you have your items sorted in the right order, and this is the first one, the third, the second one, the third one, whatever. And when you say I, when I reach item I, you have already, you no longer have W. Okay, you have W minus, for example, when you start, if you get item I into the backpack, you would get item I into the backpack, but you would have only this weight left, W minus the weight of item 1. That will be the only remaining weight. So that defines the problem for the next item, because then after you, let's say you get this into, then if you do that, your remaining capacity would be the last, the capacity last achieved minus the weight of item 2, and so on until you get to this item I, where if you include it, you would be left with so much weight. And if you do not include it, you would get it with so much other weight. Okay. So this is the, remember that the way to apply dynamic programming is that you assume, for example, that you have the problem solved up to some subset of items, let's say 1 to I, and then 1 to I minus 1. Let's say you have, in this case, you have the solution from 1 to I minus 1. And you are considering this object, I. So the question is, do we include item I or do we leave it out? And if we include item I, then what happens? What is the optimal solution? Well, assuming that we have the optimal solution for the first j minus 1 items, if we add item I, then we would be, sorry, here it is. If we select it, then we would have to collect the value, and this means add the value to the subtotal. You have to be running a subtotal. So if you are adding this object, collect its value and set the new weight limit, which was the weight limit so far minus the weight of the new element. Is that clear? Please feel free to ask me any questions. Now, if we do this, then OPT of I comma W would select, so works upon the solution of the best solution from 1 to I minus 1 and does these updates, okay? And we are left with a new weight limit. But if we do not select item I, then the value returned by OPT I comma W, which means the best possible value from 1 to up to I with W, I mean the inherited capacity left, it would select only the best, would be the solution for the first I minus 1 objects, because we did not include the ith element. So then the solution up to I would be the solution up to I minus 1. Does that make sense? It is important that you have these ideas clear because they are really simple. So do we take the object or do we not? If we do not, then the solution up to this step is equal to the solution to the previous step. And the available weight does not change. But if we take the element, the item, then the value changes, the available weight changes, and OPT I comma W, where W has been updated, is the new the resulting amount. Okay, so what is the cost of the problem up to I? And as you can see, we are only adding its value to the value of the previously selected items. And so this can be written, and this happens with all dynamic programming formulations, we can always write a recursive equation, which is called a recurrence, which is called a Bellman equation also. This name Bellman is just, it's an important name in operations research, and it has been inherited and to dynamic programming. So when you hear in an exam about a Bellman equation, I mean this, okay, a recurrence. So the value for the optimal value for any subproblem up to item I, comma W, where we understand by W the remaining weight, the available weight, then would be 0 if I equals to 0. But if I mean, if the backpack has more than 0 items, then it would be given by this. Up to I minus 1, OP of I minus 1 W is the answer, is the correct answer if WI is bigger than W. So what does this mean? This would mean that we are trying to include an item that would make us exceed the remaining capacity, because we're remember that we at any time we have the current maximum capacity is W. Okay, so current maximum capacity left is W. So what if W, if the weight of item I is bigger than that capacity, then we cannot consider that. So the optimal solution up to element I would be the optimal solution up to element I minus 1, the previous one. And that makes sense. That's just common sense. But what if it did fit? If this if statement comes out false, then we need to make a comparison. Okay? We need to compare what is bigger, to not include the item. This is the term that represents not including the item. Okay, not include. Then this would be the answer. If we include item I, then this is the answer. So the optimal solution up to I minus 1, when the capacity has been changed has been reduced by the weight of the current item we're trying to get into, and this would be incremented by the value of the current object. Okay, so this is the Bellman equation. As you can see, if you program this, if you think of it as a function, then you would be calling the same function in either in the right hand side of the equation, which means that if you want to get this value, you then need to get this value first, or this value first, these values first. And well, so what do? Well, you call the function again, but now with these smaller parameters, and it will result in a smaller subproblem, and so on until you get a trivial subproblem and pop up back from recursion. And we saw also in the last class that recursion is not really the answer, the right answer. We can apply memoization to store all those values that we are computing, and as the computation goes. So whenever we need them again, we do not need to recompute them. We just look up a table, and that is can be done in constant time.
Professor?
Yes.
Before you move on, it's probably not super important, but in the part that says goal and it has a capital W, why is it capital?
Oh, well, all questions are important, Becky. This W is capital because it is the initial capacity. It's just that if you look at a previous, let's say here, should have been said sometime. Well, it's not.
Yes, I just didn't see it anywhere else, so I wasn't
No.
sure why.
Yes, it is not. You're right. It is not told, but it is a. It is a. It should have been told, but it is, in this case we can see that it is the initial value. So W is the weight of the. This is the 11 kilograms. That's W. Oh, here it is.
Oh yeah. All right. Thank you.
Big W equals 11. Okay. So yeah, there it is. So yeah, no, the slides are not that bad. And they are incredibly succinct. I mean, brief. If you just were to see some other algorithms, books and algorithms, in fact, they would like to. I was taking a look at this one. I don't know if you can see that. Well, I will show it to you. There are some other approaches that would take like 10 pages to explain this. But the so this is the scheme. I hope everybody can have an understanding of it. Here are the Bellman equations rewritten for reference, and here's the code. How would we code it? Well, let's name the program or the procedure. Let's name it knapsack, and the input would be the number of objects, the initial weight capacity, and then all the weights of each of the items and all the values of each of the items. So the first thing is initialize your array in which you're going to hold all the partial information that you would need to store. And remember that we will have a two-dimensional array because we have two parameters. So a two-dimensional array is nothing else than a matrix. So you will have your matrix, which is M, and you're initializing 0, W, but in the beginning W0, so you would have first element 0, 0 would be initialized to 0. Okay. So that's the and then the for loop runs from 0 to W. So you would have 1, 2, 3 up to W. So you would have all these guys initialized to 0. Okay. And that's it. It's just get the first line equal to 0. Then for I equals 1 to n, okay, then we have a nested loop for each item. You can think of it as the item. Do the following: run for W equals 0 to W equals the limit. In our case, it would be 11. Then do this. Okay, do the comparison. Is the weight of you do this in the first row for item 1. So you would have another row for item 1, another for item 2, until the last item, which is n. So you would be comparing the weight of item I against each of these weights, 1, 2, 3, 4, because this loop runs from 0 to W. So you have against 0, against 1, against 2, against W. And what happens? Well, if the weight of item I, the item corresponding to the current row, exceeds the available weight, then we do not take it. So we just can downright copy the solution for the first I minus 1 with the same capacity limit. Okay, so nothing changed because I'm not taking item I. So, but how does this look like in any particular place in the matrix? If you look at as I as the vertical coordinate, so the rows, and W as a horizontal coordinate. So the columns, rows and columns. These are the columns. So I row double the column. Then we are effectively copying, just copying the row above. Whatever you had in the row above, you just copy it to the current row. But if it turns out we can fit that object within the available weight, then we need to ask this question, okay? Is the solution, which means the solution for the problem to the up to the previous point bigger than this one, then this would be the answer. You need to compute the maximum of these two items. Now this item is again just the item above the current cell, but this item is something different. It is the you would have to look at the row above, but the column would correspond to whatever weight you had diminished by the weight of WI. Okay, so you're shifting and you're looking for in any particular row, whenever you are filling this matrix from the top to the bottom, from left to right, then you are asking a question: is this element are these, let me get it. The comparison would be between this element and some element to the left. How far to the left depends on this difference on W minus WI. But one thing you know, that it is the same difference for this object, for this cell, as for any other cell. So you can sort of program it very easily, or even solve it using a spreadsheet, and that's so you can really simplify the problem. This is the way to visualize that. So you're always, this is the cost of not including element I, and this is the cost of including, the value if we do not include I, and this is the value if we do include I. So which is the best? That is the answer. That's what you write on an IW, okay? This is the IW. So we go through these two loops. So this one makes sure that we cover all the items. So you go through all the rows except the initial row. And this other for loop just scans all possible values from 0 to W, okay? And then so if we preserve this order, it is clear that when we reach any cell, we have already computed this other element because it's in the previous row, and this other element also because it's all again in the previous row, and even we computed that even earlier. So we have everything we need to compute the value for each new cell, as long as we keep the order from top to bottom, from left to right. So this would be it. So what happens in the end? What would you have here? Either this value or this other value plus the update. Okay, so the value for this cell plus the update you need to do plus this update. Okay, so how does it look like when we? How does it look like when we make a table? Okay, so this is the problem, and this is the corresponding table. So we write the Bellman equations, and well, you can see that the solution will reach a 40, but ordinarily I mean, the best way to convince ourselves that this can be done is if we do that by hand. But maybe you don't want to expend such a time. I don't know. Let me check. Let me see if I can. And we can use a spreadsheet to make this thing really work. You can try opening a new spreadsheet I mean, it can be a Google spreadsheet, or it can be any other spreadsheet that you're used to work with. And so let's work on this problem. I think we need to, I will need to add a column here. It's a convenient thing to do, to add a column for the 0 and just initialize that to 0 also. And then let's begin again. So the first thing is, okay, this is the, again, we need to write the maximum between the previous solution and the maximum between the previous solution when we include the object, which is object 1, it has a weight of 1, would be looking at column 0. Column 0 plus the value of object 1, which is this one. And then we need to add a $sign to this one so that the formula doesn't change the column. Otherwise, it would be shifting columns. And then we can just propagate this all the way to 11. So when we go to the next element, 2, it has a weight of 2. So the first point in which we can include that element is when we have a capacity of 2. So here's where we can write the formula, the maximum formula. Maximum between this solution and now what is 2 minus 2 would be 0. So we would be looking at this column 0 of the previous row plus the value for this item, which is this, the same value for all items in the row. And then we can fill. We get these 777. Okay. Then the next item 3, which is 3, that's a weight of 5. And the first point in which we can get it in is here. So here is where we will write the formula for maximum between this element and this point plus a $sign or plus the value for this object, which is 18. Need to absolutize that row. The formula gets this way. And then for item 4, we need to consider it has a weight of 6. So we go to the 6. And this is where we can write, okay, the maximum between this solution and this element plus is 22, this value. And I hope I'm not making a mistake in the values. This. And so the last element, which is 5, has a weight of 7. So here would be the first case in which we would be executing the maximum comparison, the comparison between this and this plus the value of that object, which is 28. Then, okay. Now let me just check for sanity that this is in 7 and 6 and 5 and 4 and 3 and 0. Okay, and what happens with these other cells? Well, these cells would copy just copy the 1. Oh, no, we're not, sorry, we're not copying the, sorry, I need to just copy the ones above. I would just copy 1, and then if I want to write a formula, so I have to copy 6 also, and that way, and then copy 7, and then copy the number that I formula in here, also 7, and copy all the way down. Here I'll be copying the 18, and the 18 here. Here I would be copying the 22, and this would be the table. Okay, so if you compare that with the table given in the slides, let's see. Sort of get the same result, the 40. Okay, now we have made it to this place. This is the cost of the solution, but what is the solution? Well, in each of these instances, we need to check the following. Okay, so there's always one algorithm to represent the to get the solution. I think it is not here, the backtracking is not here, but we can do that in the following way, which is where is this 40 from? Is it the same as the value above? If it's the same as the value above, we are not taking this object because because the solution obviously came from the previous value. So here we have a change, and it means that we're taking this object. So I will mark it with some formatting. So I will fill it with red, let's say. And then we need, meaning that we are taking the corresponding element, the 4. And then from this cell, since I have a change up here, it turns out that I need to go to the previous object at column 6, N6, at cell N6, which is, at cell G5, which is this one, the one told by the formula. Okay. Excuse me. Excuse me, I will make a pause. I need to take this one. Hello? Yes? Oh, thank you very much. Well, thank you. You're welcome. Thank you very much. Thank you so much. Bye-bye. Okay, so sorry, I'm back. So from here, let me get from here and finish the exercise. From here, we now are comparing this against this one. Since we have a difference, we are taking this element. So this means that we need to color it, or let me color it. We're coloring the background. Then, you know, the next cell to compare or to refer to would be B4. So we go to B4. So this is B, and this is the 4. And this, we reach 0. When we get 0, and when we get to this column, we do not take the element because it has the same value as the above element. So the only items that we are taking are these two, 3 and 4, and their weights are 18 plus 22, which is where the 40 comes from. And that is the answer. So I will edit the video and make it shorter so that you can see how to solve this in a spreadsheet. Okay. If anyone is left, are there any questions?
Professor, the rubric
Yes.
says the final is worth 15%. Is that still the case?
I changed, yeah, let me go to yes. Has changed. This is the policy. I hadn't updated it, but this is it. So between the midterm and the final, you have 35%. And for quizzes 1 and 2, we'll count 30%, lab 0, 25%, and attendance 10%. Does that answer your question?
Yeah, thank you.
What do you think about that?
I think it's fair.
So do I. I just hadn't updated it, and since we haven't had, I'm adding this other quiz. So be ready for the quiz. Now, I'm sorry. I will post this video as soon as I can, but right now I have an appointment at 5, so there will be no office hours. I'm very sorry about it, but I will connect as soon as I get over with my appointment, probably in a half an hour. So, well, this is the way we can solve the knapsack in
When is quiz 2?
quiz 2 is due on, I think it's on Thursday. Look at the dates in the Moodle.
Yeah.
Or I'm telling you there.
Okay, thank you.